Hi everybody, so here we're going to go over the terms for chapter 16, which deals with waves. So the terms we're going to look at are going to be period. Variable is going to be a capital T, measured in seconds. Next is going to be frequency. The letter is going to be a lowercase f, measured in hertz, Hz. Length, that's a lowercase l, measured in meters. And then there's wavelength, which is the Greek letter lambda, measured in meters. Wave velocity, that's VW in meters per seconds. Temperature in Celsius. So this I'm calling TC, measured in degrees Celsius. The velocity of sound, it's going to be VS in meters per seconds. And source frequency, it's going to be F sub S, measured in hertz. And then receiver frequency, or received frequency, and also measured in hertz, but this one is going to be F lowercase r and measured in hertz. And the formulas for chapter 16 are frequency is going to be 1 over the period. Period is going to equal 2 pi, and then multiplied by the square root of length over g, where g is 9.81. And the velocity of a wave is frequency multiplied by wavelength. Velocity of sound, or the sound wave, is 331 plus 0.6 times the temperature in Celsius. And frequency received equals frequency source, and then multiplied by this whole thing, which is velocity of the wave divided by velocity of the wave plus or minus velocity of the source. So these are the terms and equations that we're going to look at for chapter 16. And here we're going to talk about the vibrations or oscillations. So what the picture shows you here is you have a support system here, and then you have a spring. And at the bottom of the spring, you have a mass that's attached there. And what we're going to do is we're just going to flick the mass, and the spring is going to vibrate up and down. And as it does, we're going to graph how the height changes with time. So we'll have the vertical axis, that's going to be the height y. And on this axis, so starting from your base point of 0 here, this is going to be time. So as time goes by, you're going to flick the spring, the height is going to go up, but time is going to take in that direction. So it'll do something like this, and then the spring is going to go down, and the spring will go down to some minimum, and then it'll come back up, and then go back down again, and then come back up, and then that's going to repeat. So that's the basic point there, is that after a while it's just going to repeat. So instead of talking about the entire length of the vibration, we're just going to talk about this section that repeats. So if you look at it here, we can identify some repeating points. So here you're at 0 and you're going up. Here you're at 0 but you're going down, so that doesn't repeat. But here you're at 0 and you're going up. So this is going to represent section that's being repeated there. You have one up part and one down part. So here, this is going to be the time for one repetition, or the time for one cycle. So I'm calling that T1 cycle. And you can notice another one here also. It's kind of hard to see, so I'm going to erase this one over here. Just redo that. So another repetition would be over here. So here again, you're at the 0 and you're going up. And then here, again, you're at 0 going up. So these 2 points repeat also. So I can block these two out over here. So all you need to do is, instead of looking at the entire wave, is just talk about the time for one cycle, and everything else repeats. So that's going to be our first definition. We're going to say that a wave's period, or capital T, is going to be the time for one cycle. And there's another way we can look at this. Instead of talking about the time for one cycle, we can just say how many cycles does it make each as time goes by, and that is going to be called the frequency. So frequency is just going to be the number of cycles that you make per second. So I forgot here, period is going to have units of seconds because it's a measurement of time. Frequency is just going to be a number per second. And so I'm going to write the equation first. So the equation is pretty simple. It's just the frequency of a vibration is 1 divided by the period of the vibration. And from there, frequency is going to have units of hertz, or capital Hz, or it can also have units of 1 over seconds. But normally, you can describe this in terms of hertz. For sonography students, sometimes you'll see it in terms of kilohertz, or even megahertz. Or it will be something like this. Megahertz would be MHz, and then kilohertz would be KHz. So let's look at a sample, or a demonstration of this. Okay, so we're not going to look at the entire simulation. We're just going to look at oscillations and look at the different components. So the first thing is we can change the height of a wave. That's going to be the amplitude. So this is a big height, so that's a big amplitude. And we can drop the height down to a small value. That's a small amplitude. So in terms of sound waves, that would be a big amplitude would mean loud, and a small amplitude would mean quiet. And for light is another kind of a wave, or a large amplitude would mean bright light, and a small amplitude would mean dim light. So that's the first part of a wave. The second part is going to be how fast the wave vibrates. That's going to be the frequency. So if I go to a low frequency, it vibrates very slowly. And if you go to a high frequency, it vibrates very fast. So here in 1 second, this says 3 hertz. So in 1 second, this thing vibrates 3 times. So the next simulation, or the next concept that we're going to look at continues with this idea of vibrations, but now in terms of what's called a pendulum. So a pendulum is another support. And here what you have is just a string, and you're just going to move the string off to the side and then let it go. And when you let it go, it's going to vibrate back and forth. I forgot to mention that at the bottom of the string, you're going to tie a mast to it, or some kind of a bob, to keep the string tight. So just move it off to the side, let it go, and it'll vibrate back and forth. And here the main terms are going to be just how long the spring is. And given just that, you can actually figure out how much time is it going to make to make one cycle. So the time to make one cycle would be you let it go here. It will be the time for it to come back to your hand. So that's going to correspond to the time for one cycle, or the period. And the equation is pretty simple. If you're on Earth where gravity is pulling downwards on you, the equation is just going to be 2 pi, and then multiplied by the length of the string divided by g. So let's look at a simulation for this one. So as this load, I'll just tell you that G is 9.81. That's going to be a constant. So the only thing that changes here is going to be the length and the period. So let's see that. So you have a basic system here. So I'm going to displace this pendulum a little, and you'll let it vibrate. So that's the time for one cycle would be the time when it comes back to the right. So the only thing that really is going to change things here, besides gravity, we're going to leave gravity the same, is I'm going to change the length of the string. So if I make the string long, you'll notice that it's going to vibrate a little slower. And the shorter I make the string, the faster it vibrates. So that's the basic concept. If you change the length of the string, you're going to change the time for it to make one cycle. And this equation describes that. So all you need to plug in is the length, and this is going to give you the time for it to vibrate.